Today we are going to discuss a critical yet often overlooked parameter in the blast furnace operation, the MICOM 10 index. We will see how even a teeny deviation of just 0.1% can have a significant and costly impact on efficiency. It is not only the efficiency which further leads to productivity loss and our bottom line also. So let's begin. First, what exactly is MICOM 10? Simply put, MICOM 10 is a measure of coke strength. It represents the percentage of coke that break down into fines pieces smaller than 10 millimeters. After a standard abrasion test in a MICOM drum, a lower MICOM 10 value means stronger, more resilient coke. Conversely, a higher MICOM 10 value indicates a weaker coke that generates more fines, which is the root of our problems and mostly 99% problem of the blast furnace our stack area. To put this into perspective, let's consider a real world plant scenario. Assume a blast furnace producing 8,000 ton of hot metal per day with a coke rate of 400 kilogram per ton of hot metal. That means the furnace charges 3,200 tons of coke every single day. Now let's see what happens when MICOM 10 increase by just 0.1%. On our 3,200 tons of daily coke, a 0.1% rise translates directly to 3.2 extra ton of fines produced every day. Scale that up over a single month, that's a 96 ton of additional problematic fines entering the blast furnace system, and which is no less to create bigger problem. These fines don't just disappear, they enter the furnace and begin a chain reaction of operational issues. First, the fines fill the voids between large coke pieces, blocking the channels for hot air and gases to flow upward and interrupting the smooth drainage of liquid iron and slag. This leads to a rising pressure drop across the burden. To compensate, operator must increase the blast pressure, which consume more oxygen and energy, driving up cost. Finally, this creates a serious productivity risk, increased chance of channeling, irregular burden descent, and may even force slow downs or unscheduled stoppages to recover all these problems. Now, the consequences are both economic and operational. More fines means a waste of our carbon resource. It reduces hot metal productivity and increase of a specific coke rate. On top of that, you incur extra cost for handling and disposing of these fines. If not addressed proactively, then these losses multiply very quickly. Now let's look at a quantitative impact backed by studies and plant experience. A 1% volume increase in fines can reduce bed permeability by 10 to 20%. Even a minor daily increase, when persist, reduces the overall permeability within days. The resulting pressure drop forces a difficult choice: either increase blast pressure, raising power and oxygen cost, or reduce production rate. The observed consequences are very clear. Lower permeability leads to less efficient combustion and reaction, forcing a higher coke rate. In severe cases, you may need to reduce the furnace burden. sacrificing hot metal output, and there is always the risk of emergency stops if the furnace become badly choked. So, for our example of a 0.1% micum increase producing 3.2 extra ton of fines, the coke bed permeability drops by about 1.1% and the pressure drop increase by similar amount for a large production of blast furnace. This is immediate and significant. It demand higher blower power, risk gas flow disruption, and can persistently force down production rate and yield in a big way. Now, this brings us to the direct cost. To compensate for that 1% rise in MICAM 10 and maintain normal operation, the coke rate must be increased. In our case, from 400 kg per ton of hot metal to 400.4. The key message is that a 0.1% increase in MICAM 10 require 0.1% rise in coke rate, directly raising fuel consumption and production cost. Now our summary table put it all together. A 0.1% MICAM 10 increase leads to 1 to 2% permeability loss, a 1 to 2% higher pressure drop, and a direct coke rate increase. If MICAM 10 rises by a full 1%, the impacts are an order of magnitude greater with significant cost implications and especially for the large plants. Now, the takeaway is clear. Even a 0.1% MICAM increase create enough fines to significantly choke the coke bed, risking pressure buildup and reduced throughput. Bed permeability is highly sensitive to fines generation. We cannot let a small MICAM change and slip by these is a really very difficult task for the blast furnace. So, for management, the message is that there is no such thing as a small MICAM 10 increase. Every 0.1% rise creates 3.2 ton of extra fines per day. Have over month, this represents a significant output loss and a constant operational burden directly impacting profit. This demands a proactive call to action. We must implement continuous quality monitoring, focus on MICAM 10. We need to link MICAM 10 values directly to furnace KPIs and profit metrics. And we must prioritize process adjustment and super quality assurance to maintain low MICAM 10 at all times. Vigilance here is a direct lever for profitability. In conclusion, remember these visuals. Coke fines lead directly to permeability reduction, pressure drop increase, and a higher coke rate. Managing MICAM 10 is not a minor technical detail, it is a fundamental strategy for a stable and cost effective blast furnace operation.